there again, so you can get practice doing it. And then that will sort of wrap up chapter 10. That way we can kind of start with chapter 4 there on Monday fresh and all that good stuff. And then we'll do the experiment, which isn't a very long experiment, I don't think. So that's sort of the game plan here. So what I want to do is, again, I went through it sort of with my sort of approach there as to how to do it. And I think it's very similar to what we'll see here, but I'll just kind of show you the prettier written version of what we just did there. And again, walk you through sort of what you want to do when you kind of approach these sort of Hess's Law type problems, and sort of really, the kind of the simplest sort of thing that you want to do. So in this problem that we just kind of completed there at the very end of lecture, what we had were these two equations. And really what we had with these equations were they were actually reversed. So if we went back and you looked at the original example, both of these reactions were basically opposite. So we had the NH3 going to the 1/2 of N2 plus the 3/2 H2. And on the other one, we had 2H2 plus O2 went to 2H2O. And again, the first thing that we really want to do is sort of reverse these reactions. And really, it's because when you looked at sort of the reaction that you were trying to build, which is sort of this guy on the bottom here, we had the NH3 on the right-hand side, and we really had the O2 on the right-hand side. And in the original equations, these guys were on the opposite sides. So really the first thing that you could do is reverse both of them. And if you look back at the original problem, what you'll see is we did change the sign on both of the delta H's. And again, that's what you do always when you sort of reverse a reaction, delta H value changes. The next thing that you want to kind of look at is, like we talked about, you want to make sure that you have the correct amount of everybody. So now that we sort of got everybody on the right side, either left-hand side or right-hand side where they need to be, as I mentioned earlier, we have only one NH3 in our original sort of equation, but we did need 4 of them. So that's why we then multiplied this top equation by 4, because that will give us 4 of the NH3s. In addition, the bottom guy, the O2 had 3, but we only had 1 in this equation, which is why the next thing that we want to do was multiply the bottom equation by 3. And again, what we're just trying to do here is really just build that overall equation from these two guys. And that's what they did next. If you look at it here, they multiplied the top guy by 4. And again, the purpose of that was to get us the correct number of NH3s. And they multiplied the bottom one by 3 to give us the correct number of O2s. And what that does to the delta H values, as we talked about, is we also need to multiply the delta H values by those numbers as well. And when we do that, what that's going to do now is give us the correct amount of everybody that we need. And if we do that here, multiplying it here, and we can see our adjusted numbers, now we have the right amount of NH4 plus our NH3 and the right amount of O3. We're ready to now add these guys together like we did. And again, anything that's on opposite sides of the arrow, so for example, the H2 is on the left-hand side of the arrow in the first equation, and it's on the right-hand side of the arrow in the second equation, they will cancel each other out. It's kind of like when you have 2x equals 2x. You can kind of think of the arrow as an equal sign. You would subtract 2x to both sides, right? And they will cancel out. So it's the same idea when you're adding equations together. If you have things on opposite sides of the arrow, they also reduce. So same idea, if you had 3x equals 2x, you take minus 2x to the other side and be left with an x, right? And same idea, if I had like 6 H2s on one side, 5 on the other, I would be left with 1. So it's sort of like subtracting it to the other side, and that's how they cancel. And what that leaves us is, as we talked about here, the overall reaction that we wanted. We have the 2 N2s on the left-hand side. We have the 6 H2Os on the left-hand side. We have the 4 NH3s on the right-hand side and the 3 O2s on the right-hand side. And to get our final amount of energy, after we correctly adjusted all of these values, we simply add them together. So when you take the 1452 and you add it to the minus 184, that is how we get to our number down here by just simply adding those together. So sometimes people get, again, kind of really overwhelmed by this, but again, just keep it simple. Just try to get things to the right side, adjust things. And the really important thing when you're doing this is, you know, you got to sort of keep track of what you did and how that affects the delta H value. So the easy way to do is sort of like this, and sort of what I did is step by step, as you change something, change the value of the delta H. That way you don't have to remember at the end, oh, I flipped it, I multiplied it, I divided it, and try to remember what you did. So as you keep changing the equation, change the delta H value correctly, and then you should hopefully end up with the right one at the end. Question on that there.
So you get the desired reaction like always, and then you're just supposed to find out how to find the enthalpy, or
Yeah, so in a question like this, if that's what you're asking, in a question like this, they'll typically always give you like, this is the equation you're looking for, and then they'll give you these several individual equations. And it really is just, you want to take those several individual equations, move them around, sort of manipulate them. And sometimes you don't even have to do, in some cases, anything to an equation. You can just leave it the way it is. And you want to do it in such a way that when you end up adding all those individual equations together, it gives you that desired equation. And you're always going to be given that reaction in a problem like this. They'll always tell you, hey, this is
okay.
sort of the reaction that you're looking for.
So
So you
we'll
not,
never have to solve for enthalpy, like just not or solve for the desired reaction by just having
no, so
that.
not in the sort of a Hess's law type problem.
Okay, got
They'll always give you like, hey, this is your goal. This is sort of what you're trying to find, and then they'll give you all the individual ones. And really, for this type of thing, the only thing you have to worry about is just keeping track of what you do to all those individual ones before you add them together.
it. Okay, thank you.
You're welcome. Other questions on that? Okay, so why don't we try one more here just to make sure. So again, our desired equation there is on top. And again, we want to build it based off of these two and try to figure out what the delta H value is. So take a couple of minutes there and see what you come up with. And again, try to keep track of what you're doing, change the delta H values. And when you're all said and done, all you have to do is add up the delta H values and see what you come up with. So let's take a look here and kind of see how we're doing. So again, you really just want to kind of keep it simple. It is as simple as I just need to get everybody on the correct side. So that's a good way to approach it. So for example, here, if we look at our first one, I have SO2, and again, this is our desired equation, which will always be given to you in these type of problems. So I want to get the SO2 on the left-hand side, and the only one that has SO2 in it here is the first equation. And what I see is in the first equation, it's on the right-hand side, which means that is not the correct side. So I definitely need to reverse the first reaction. And when I reverse the first reaction, that just means everybody on the left goes to the right, everybody on the right goes to the left. So it's going to rearrange and be reversed and look something like this. Now, when we reverse a reaction, the actual sign of the delta H will change. So it started at negative, and because I reversed it, it will now become positive 297 kilojoules. Any questions on that first step there? Now, when we look at what's left of our equation that we're trying to find, we've obviously already kind of used the first equation here. So that's going to leave us the second equation to work with. We have O2, and it is on the left, and I do see O2 on the left, so that's okay. But more importantly, when I look over here, I see SO3, and SO3 is also on the right on both sides, which is good. The difference, though, is in our desired equation, we have only one of the SO3s. In the equation that was given to us, we have two of the SO3s. So what that means is for the second one, just simply to get us to the correct number of SO3s, I need to take everybody here and divide all the coefficients by 2. And if I do that, I'm going to leave the reaction the same way, which means I'll end up with S plus 3 divided by 2, O2, divided by SO3. And that's what I get when I come across basically and divide everybody in that second equation by 2. Yeah. And what that does to the delta H is for the second equation is I didn't reverse it, so it's still 792. But what I did do to it is I divided it by 2. So I need to take that delta H value and also divide it by 2 because I divided everybody in the equation by 2. And what that's going to give us for our delta H is 792 divided by 2 minus 396. Any questions on that there? So when I'm ready now to add these together, which at this point I pretty much have done something to both of these equations, there's nothing left. I'm going to add these together. And anything that's on opposite sides of the arrow will cancel each other out. So for example, here on the right-hand side, we have an S. On the left-hand side in the other equation, we have an S, so they cancel. The 3/2 O2 and 1 O2, so those will not completely cancel. So I have 3/2 O2 on one side. I have an O2 on the other side. That is the same as 2 divided by 2, right? Which if you bring this to the other side, will leave you with 1/2 O2 if you subtract that to the other side. So this will cancel on the right. This will now become 1/2 O2, these two. And that will leave me with SO2 plus 1/2 O2. And on the right-hand side, all I have there is SO3. So by rearranging the first equation, by reversing it, by dividing the second equation by 2, and then adding together, we have now successfully built the equation that we were looking for. Any questions on that there? Now, to find the delta H for this equation we just built, we've already adjusted all of our delta H values based on what we did to it. So we simply just need to add those numbers together. So that's going to give us 297 plus a negative 396, going to give us a negative 99 kilojoules as our delta H value. The negative here will tell us that this reaction is exothermic. Question on any of those steps there. So I just highly recommend to just keep it really simple, just left side, right side. I need to get everybody to the correct side. You will, so the question is, will you need to always reverse a reaction? You won't. There's some Hess's law problems where, for example, you're given, say, 3 equations or 3 reactions or even 4 reactions sometimes. Sometimes it's crazy. You got like 6 of them or something like that to build it from. But sometimes you're given multiple reactions, and in certain cases, you may not even have to even touch one. You could leave it exactly how you find it. So you don't always have to reverse a reaction. And in this particular example, we just did on the second equation, we didn't reverse it. The only thing we did to the second one was divided by 2. So we kept everybody on the correct side. So you don't always have to reverse a reaction. Again, you just need to do that if somebody's on the wrong side. So you just gotta kind of flip them around to get them to the right side. So you won't always have to do that. And like I said, there'll even be cases where you may not even actually touch anything in terms of the equation, may leave it exactly the way you find it, and everybody will be on the correct side. Question on sort of Hess's law, how to do this, any questions like that? I divided by 2 on the second one because before I did anything here, in the equation that we were looking for, the SO3, the coefficient of the SO3 was 1. In this equation that was given to us, the coefficient of the SO3 was a 2. So what we needed was just one of those. So that's why we had to divide everybody by 2 to get us to 1. And that's why we divided it by 2. The second equation was ultimately to get us the correct number of SO3s. Done with chapter 10. This is as far as we're going to go, I think, in chapter 10. All the other stuff you don't have to worry about on